It's better we move on with the next.
Sure.
With Matteo Vitturi from Italy. He is going to present Z80 for the Spectrum computer.
Great. I'm looking forward.
Thank you, Ulrich.
Sure. You're welcome.
We cannot hear you, Matteo. Your microphone is off. Your microphone.
I think you're on mute, Matteo.
Perfect.
Yeah. Can you hear me now?
Yes, yes.
No. Yes? Okay.
Yes.
Looks fine.
Sorry, I couldn't find the control. Well, I hope you can see my share. Well,
Yes.
okay. This what you see now is the emulator of the ZS Spectrum Next. So I use directly FORTH to show FORTH. Okay, because FORTH in my life is I use just to play games and not for professional use. So let's start. I started when I bought my first computer. Well, then in the 90s, I disassembly white lighting FORTH. Then I tried to implement the ZX micro drive. So I just recompile everything to work with the micro drive. Do you know why micro drive? I think you know that is the worst mass storage unit available in the market. But this is what I got in the 90s. Then I had to, because the Spectrum is very fragile, I had to put aside everything. But I found emulators that works with micro drive, and so I restarted this FORTH. This is my passion because I don't use FORTH for professional. I use other language, but I have to breathe some FORTH every so. I continuously improve this FORTH for my pleasure, and then in 2001 I found Albert van der Horst work. It is an 8080 Intel assembler and disassembler altogether. But what I need was a Z80 assembler. So I simply filled the gaps between 8080 and Z80 to obtain an assembler. This is a people say that this is a very nice piece of software I ported. I did not write it from scratch. I simply improve Albert's work to do his job. And so I also ported to Disciple version. Then when I got my Z Spectrum Next, I could port on a total new computer. So inside the SD card of the Spectrum, I structured things like that just to know. The memory map, okay, let me say a few things. The new Spectrum Next comes with a huge amount of RAM that you can split, you can fit in 8K page. So reading from the bottom, I use the last 8K page to fit all the RAM available. Then I had to scrunch everything to fit the FORTH itself to work with the Spectrum, because I didn't want to lose the feature of the Spectrum itself. So let me continue. In the years, I developed some utilities, for example, an full screen editor for blocks and screens. And then I developed the C and the assembler. Then when I had so much memory available, I also invented some heap utility. I also, I also implemented some interrupt routine and to see how it works. The floating point option is available, but is the ZX Spectrum original one. I simply use the ROM routine available. And then I found also some standard test to prove that this fort is quite standard. Well, let me see something. I already did some loading beforehand, so we can show what. Okay, I'm just showing you a few seconds of game. This is written in Fort. Simply. Okay, just to say, sorry. Okay, and for example, I had another thing that was to show color picker. This is sorry, the wrong palette. I had to reboot everything. I'm sorry. I'm sorry. This is the live problem. Okay. Sorry. Okay, let me explain a few minutes about the assembler, because it's very fun, very useful how I can define words and opcodes and write in assembler that is quite very similar to the original Z80 syntax. So the push IF and a dash is a Fort definition. So for example, I had to define the family of the registers and the opcode, and then I can use them to code using a Fort assembler directly. And this is another example of how this assembler is coded. It's very similar, in my opinion, to the original syntax of Z80. So you can see that you can just remove some space and remove some comma, and it is exactly the right syntax. I had to, for example, I had to specify that the argument is number of address to be sure that the syntax is correct, but it's just what I follow in the Albert's work. Okay. For example, I code the dope duplication word exactly like that. It's, what you can see in this Fort that I use the index register IX to contain the next address of the inner interpreter. So this led me to a vectorized jump to the inner interpreter that allow me to implement a trace utility. For example, if you change the address of IX at runtime, you can change the behavior of this Fort. This is not my idea. I stole this idea from Marcos Cruz from Spain, I think. Anyway, this is jump IX is faster than just a simple jump, because JPIX is 8 t-state. Instead, a normal jump is 10 t-state. Okay. Then the last thing I want to say is that in the beginning, I code this Fort using an indirect threaded code. And this is what you see now is the inner interpreter. In the right was the old indirect version. In the left, you can see the new direct that spare some tick states. So everything is faster, but you have to spend some memory to do the jump. For example, the enter routine needs a call enter to perform everything, and I saw that the overall payoff is between 39% of faster, between and 9% faster. It depends on how the words are shared, because if every word, every definition is written in machine code, then you have the maximum gain of speed. Instead, if you have to enter, like normal, everything column definition does, you lose some speed performance, but it's not so bad. In average, I saw that the direct versus indirect, you gain something 25% of speed. Okay, that's all. Let me try to. I don't know how to stop my share. Help, Peter.
So if you move up, there should be a green bar, and below that there should be something that says stop. But if you don't, yeah, no, that's
no. This is my desktop. Sorry.
But I can do it for you.
Let me. Sorry, I lose my control. Sorry.
Oh, that was not it. So I switched off your camera. So I'm sorry about that.
Sorry.
Like this. Here we go. Thank you very much. So please switch on your camera again, and maybe there are some comments and questions on your talk. Thank you very much.
Matteo.
I really enjoyed this, especially